So this is our original circuit here. And the first thing I'm going to do is redraw that to make it more straightforward and more kind of traditional to look at. So I've gone from that to this. So I've moved my R1 round the corner here, so it's still in the same current path, no junctions between the supply and R1. Then after R1 I've got this junction here, which is the same as this junction here. Then taking one of the current paths from this junction takes you through R2, then back to the supply. So that's what my new circuit does. My other current path takes me through R3 onto this junction here, which is this junction here, then splits through R4 and RL, R4 and RL, takes you back to that junction there, and back to the supply. And to reduce this to get our total current, I would start off by taking these two resistors and finding out what the equivalent parallel resistance for that would be. And that's what I've done here. So I've worked out that my RP would be 3.6. So there it is there. So I've replaced these two by this 3.6. Then my next step would be to replace these two by an equivalent 1 resistor here. So 8 and 3.6 are in series, so you just add them up. That gets you 11.6. Then looking at that, my next step would be to combine these two resistors in green, these two that are in the green loop. They're in parallel, so I'm going to do the product over the sum again. And that gets you this value of RP2. So looking back at that, my values were 10 ohms and 11.6 in parallel. 10 and 11.6 in parallel gets you 5.37. And then in yellow, my final loop is to get my total there, 9.37. So once I have that, I can then start looking at calculating out my currents. So my supply current, which would be my current there, or there, or here, 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 or here, is going to be calculated by doing your VS over your RT. So VS over RT, so it's 8 for your VS, and your RT is that value there that we've worked out, 9.370. Here's my 0.8538 rounded amps. So that's what I've got for that. Now that would be the same current through all of this, and it would also be the current that would come down here and hit this junction. So if I was looking for this current here, and I'll call it IRS, to work that out, I would use a current divider to do that. So that's what I'm going to do. IRS, I'm going to use a current divider for that. So if you remember, current dividers is the current entering the junction you're dividing, that's IS, times the resistance in the opposite branch, multiplied the resistance in the two branches added together. So it's that 0.8538 multiplied by 10 divided by two things in the bottom, bracket them up, 10 plus 11.6. Gets you 0.3953. So that's my IRS here, which is my current here as well, which is my current through here. So at this point here, that's my IRS. And I'm going to use another current divider to see which part of that goes through my RL. So I'm going to do a current divider again. So this time it'll be for IL. The Current I'm dividing this time is IRS. That's the current before the junction. Resistor in the other branch is the 6 over the 6 plus the 9. So 0.3953, which is my answer from here, I've taken round to here, multiplied by 6, divided by 6 plus 9. Gets me 0.1581 amps. So 158.1 milliamps. That's my current through my load resistor. So that current there is my IL, which is that current there, that IL. It's the same. Then to get the voltage across my load resistor, V equals I times R, so VL equals IL times RL, 0.1581 multiplied by the value of my load resistor, which was 9. And that gets me 1.423 volts. And it's as simple as that.